That takes a lot of setup, so.
We would get a lot of viewers.
What's that?
We would get a lot of viewers. We get famous.
We'd share it.
Next thing you know, there's a comment from the class, and I go viral for all the wrong reasons, right? Is that how it goes? All right, everybody, let's get started. Lecture 2. Couple of housekeeping items. So I've gone ahead and updated the attendance grades from the first lecture. So if you review Blackboard, you should see that if you were here on Monday, you have 100 in the class, right? Because that's the only grade we have on file right now is the attendance for Monday. The Lecture 1 recording has been posted. It's on the YouTube playlist. So if you log into Blackboard, you will see a link to the lecture recording for Lecture 1. But really what it's doing is it's just linking to a single playlist, and so all the lectures will be there. You are going to get your first homework assignment today due on Friday. In terms of its length, it's one of the shorter assignments we're going to have this semester, and you'll see what I mean after we start doing some problems today, because we are going to start doing some in-class examples today. And our topic today is on classifying structures. And really what we're trying to do is answer two questions. Are structures stable, and are they determinate? And you will understand what both of those mean after the lecture today. I am sure that in statics or maybe in engineering 216, you probably heard the term determinate. And I think you probably did some indeterminate problems in 216. But they were probably, usually those problems are restricted to what I would call just stress analysis concepts. For example, a composite column, like a column that's made out of both copper and brass. And you have to determine how much loads in the copper and how much loads in the brass. They are indeterminate problems, and a lot of the methods that we use to solve those problems are similar than what we're doing in here, but we're looking at whole structural systems as opposed to each element. Okay, before I move on, did everybody get the code? Going once. Going twice? Did you get it? All right, everybody got it? Okay. All right. Okay, so lecture 2. All right. All right, so we're going to be talking about modeling and classification of structures today. And so remember from, it was one of the last things I said in the lecture on Monday, our first lecture, that we are not really analyzing structures, but what we're doing is we're analyzing mathematical models that represent structures. That is a subtle nuance, which admittedly we will get lost a little bit in the weeds on that later on in the semester as we just start diving into trusses and beams and frames and all that jazz. But even though we're going to just sort of dispense with the terminology and just start talking about structural analysis, the models that we analyze are going to adhere to certain rules. There's certain behaviors that we are going to assume, and we kind of need to understand what that behavior is, what those tools are. And also we need to be able to classify structures. Now, what matters to us as civil engineers in terms of structural analysis is we really want to know whether or not the system is stable and whether or not the system is statically determinate. Now, in order to determine these two, we're going to have to know about things like boundary conditions and what are internal releases and things like that. But really, these are the two big questions that we want to answer. Obviously, we don't want to be building any structures that are unstable, so being able to determine whether or not a structure is stable is important just from a practical standpoint. But whether or not the structure is determinate or not is very critical in order to figure out the type of analysis that we're going to perform. Indeterminate analyses are a lot more challenging. They're not. Actually, that's probably the wrong way of saying it. Indeterminate analyses use a lot of determinate principles, but really they're just a lot longer to do. They take a lot more time and a lot more math. And they also require more information about the structure in order to be able to do it. But I'm getting way ahead of myself. Let's start at square one. So let's talk about modeling structural systems. And a lot of what are going to be on the next few slides are stuff that you all have seen before. And you'll see what I mean in terms of boundary conditions and things like that. Okay, so in the last lecture, what we talked about was taking structures which are complex 3D systems and turning them into this, okay? The goal with these idealizations is to represent the behavior as close as possible. So I guess it's worth mentioning that when you take a complex 3D system and you idealize it into something like this, you do lose a tiny bit of accuracy. That's just the truth. But with that accuracy comes ease of analysis and really possibility of analysis, and really the end goal is the purpose of design. The methods that we're going to be using this semester, I think it's fair to say they're tried and true, and they work. I mean, I could go on and on about the research into that, but yeah. So I just wanted to again emphasize that we're not analyzing the structures themselves, but these models that represent them. One of the ways that we will model a structure in this simplification that I'm talking about, let's just talk about something pretty basic. Let's say that we have a truss bridge. Okay, I'm sure you all have seen structures like this, just even around the area. Again, this is a three-dimensional system. Okay, what we will do as structural engineers is we will take this three-dimensional system and we will idealize it into a two-dimensional problem. Instead of looking at the entire bridge in one fell swoop, we'll look at each line of trusses one at a time. Okay, this is probably the most common way of modeling a structure, is to take a three-dimensional structure and idealize it into a two-dimensional model. We do this all the time in the real world, and if I was a betting man, you all have probably done problems like this. Analyze trusses in statics or maybe strength of materials. Maybe it's been a while, but you've at least seen it, okay? So this idealization is very common in the real world. And so a couple things about the modeling that are worth mentioning is, one, the two-dimensional aspect, the fact that we went from 3D to 2D, but the other is the fact that the system is comprised of 1D line elements. So we took these three-dimensional members, these angles and channels and whatnot, and turned them into lines, just one-dimensional lines. To those lines, we assign certain mechanical properties, the fact that they resist forces only axially. We assign, a modulus of elasticity and area and so on and so forth to them numerically. But we assign to these 1D line elements certain behaviors that are intended to mimic the real world response. Okay, so let's talk about these 1D line element models, which are going to be pretty much what we do the entire semester. Okay, so one of the biggest characterizations of these models are boundary conditions. Okay, boundary conditions or maybe a simpler term, the supports are the features of the structure that attach the structure to what I'll call the ground. Okay, and the ground could be the actual ground itself, or it could be an adjacent structural element. So, for example, anybody recognize this picture? That's right out here, right? That's the canopy that covers between the old and the new engineering buildings. Okay, so when I say the ground, for example, if I'm looking at, let's say, this column, okay, the boundary condition, affixing it to the ground is the actual ground, right? Whereas if I was trying to analyze, I don't know, let's say this beam right here. Well, the end of this beam isn't connected to a ground, it's connected to the next adjacent structural element, right? And so if I was looking at boundary conditions for this beam, I would be focused on how this particular connection is going to behave, not what's going on to the ground. Does that make sense? Everybody kind of okay with that? So when we define boundary conditions, it's more about where the external forces on the structure are going to be in order to keep the structural in equilibrium. Okay. Now, one of the things that we will need to do as structural engineers is look at these boundary conditions and ask ourselves, what type of boundary condition are we going to be looking at from an analytical standpoint? In other words, if I'm looking at this column, let's say I'm looking at this boundary condition right here, this place where the column comes, is connected to the ground. Is that connected in such a fashion that we would consider that a fixed boundary condition? Would we consider it a pinned boundary condition? Or maybe more specifically, what's the difference between a fixed boundary condition and a pinned boundary condition? And it is those assignments which we're going to be responsible for as engineers, so we need to understand what those types of support systems are and what they represent. Okay, so we have three primary boundary conditions that we use in structural engineering modeling. The first is a pin support. And I imagine I'm starting to get to the point where y'all have seen some of this stuff before. Am I right? Good. Okay. So this is a pin boundary condition. When I draw this by hand, I will probably use a triangle type symbol. Okay. Here are some real world examples. So this one here on the bottom is probably more like physically what you would think of when you would think of a pinned boundary condition. This one you probably aren't thinking of right off the bat as a pin boundary condition, but I'm going to explain why we consider this a pin boundary condition here in a second. Okay? Now, pin boundary conditions are characterized by this symbol, and from an analysis standpoint, we assume they contain two unknown force reactions, a force in the x direction or a force in the y direction. Or, I mean, we could use vectors and trig to just resolve that into a single force, but basically it has two unknown components, an x component and a y component. Now, the other thing that I want you to be thinking of when you're thinking about modeling and what makes sense is not just the unknown forces, but what's going on with how this boundary condition would displace, how it would deform, okay? I propose that pin boundary conditions are boundary conditions that prevent translation but freely allow rotation, okay? In other words, if I was looking at this boundary condition here on the bottom, that boundary condition would easily rotate. Like I could easily take this element and spin it about this little bolt, but I couldn't pick it up and move it, up and down or move it left to right. Does that make sense? It's like the same thing with this door hinge here. I could take this door hinge, this door, and I could freely rotate it around this this hinge here, but I can't take the door and translate it. It's restricted from that motion. Does that make sense? Everybody okay with that? So then that might raise the question, well, why would we consider this a pin boundary condition? Well, let's take a look at this column, and more specifically, let's look at this beam. Okay, so this beam is a steel I-beam. You probably heard that term I-beam before, right? We don't really use the term I-beam anymore, and if you take steel design, we'll get into that. We would more or less call that a W shape, and we'll talk about that a little more later this semester. But if I draw that I shape, it's going to look something about like that, right? All right. Pop quiz. Anybody remember what we call the top and bottom plates? Anybody know what the flanges, and we call the center the web, right? So flanges and web. Okay. Now, in structural engineering, in steel design, this is a broad simplification, but it works pretty well. That in steel design, we tend to consider that the flanges are the component of the I-beam that primarily carry the moment, but the web is the part that primarily carries the shear, okay? So what we have is a connection that is connecting the web, but it's not connecting the flanges. So from a strength standpoint, we would say that connection is strong enough to resist the shear, but not the moment, okay? So we would say this connection would not really prevent rotation, kind of like this one, right? This one's a little bit more apparent, like you could obviously rotate this, but we're saying this connection isn't mechanically strong enough to resist that rotation. So that's why we would consider both this and this a pin connection. Does that make sense? Everybody okay with that? All right, good. Okay. Now here's a pin support. Let's talk about a roller support, okay? Now roller supports only contain one reaction, and that reaction is in the direction of the roller, okay? Now I will draw that as a circle, right? Sometimes in the textbook you'll see this little, tiny skateboard looking thing. But essentially roller connections allow translation along the axis. Commonly, they allow translation along the axis of the member. Sometimes we'll have inclined rollers, which we'll talk about actually sometime next week. Now, some of you might be thinking, just off the top of your head, wait a minute, why, as a structural engineer, why would you want that? Like, why would you allow it to move? Wouldn't you want it to not move, right? Wouldn't you want it to sit still? All right, somebody's shaking their head no, and I imagine you're shaking your head no. You've maybe been on some construction sites or whatnot. There you go. Okay. All right, I like where you're thinking. Okay, so let me tell you why we would actually want to allow a little bit of translation. I'll give you a anecdote very near and dear to my heart, and I'm sorry, you're going to hear a lot about bridges in here, so let's talk about bridges. Okay, we've been blessed with some somewhat coolish weather this week. We've had a pretty warm summer, haven't we? It's been pretty toasty, right? Okay, so it's been pretty toasty this summer. Okay, now imagine the winter. Okay, winter's going to get kind of chilly, right? That's going to be a heck of a temperature differential along the length of the year, right? We're going to go from really hot days to really cold days. So what's going to happen to a bridge beam throughout the year? It's going to expand or contract, right? What we want is we want to allow the system a little bit of flexibility to translate along the axis of the bridge. If we fix both ends, what's going to happen is we're going to induce a lot of force in the abutments or the retaining walls on the ends of the bridge, right? So we actually want a little bit of a little bit of flexibility. You'll see in bridges fixed bearings and expansion bearings, allow that rotation. They have instead of it being like a straight hole, you'll have a slotted hole that allows it to move a little bit. And we also, for example, this is probably more of a mechanical expansion bearing where it can actually roll. A lot of times in common or more modern bridge applications, the bearing system will be an elastomeric bearing. It's kind of like this vulcanized rubber pad with these steel plates in it. It's sort of like a super stiff jello, and it can move a little bit. And we kind of want the bridge to be able to move a little bit so that it can thermally expand and contract and not cause damage to adjacent elements. Does that make sense? That's just one thing to think about. Okay, fixed supports. Okay, fixed supports. You'll kind of see me draw that just sort of like with a line and maybe a little shading or a little squiggle there. And fixed supports we consider to be completely fixed. In other words, they prevent translation and they prevent rotation. Okay. They are strong enough to develop both a shear reaction and a moment reaction. Okay. Now, to be clear, again, what we're talking about are analytical models. Nothing in this world is infinitely stiff. Okay, or nothing can perfectly prevent translation or perfectly prevent rotation. But they're strong enough such that they can develop a shear or a moment for the purposes of design, and we design those connections as such. So for the purposes of analysis, we can consider those to be fixed. So as a result, they develop both a force reaction and a moment reaction. And so fixed supports in 2D will have three unknowns: a force in the x direction, a force in the y direction, and an unknown moment. Okay, does that make sense? Bear with me so far? Okay. All right, now those are external boundary conditions. One thing that's worth mentioning is an internal release. Okay, so an internal release is a point inside the structure where we have removed from the structure the ability to resist a given response. Now, analytically, we can define shear releases. We can theoretically define axial releases. The most common release available is a moment release, or a hinge, putting a hinge or a pin inside the middle of the beam. Now, there are some real-world examples of this. If you find some older bridges that have a connection that looks something about like this is called a pin and hanger connection. It actually acts as a hinge, okay? Back in the day, I mean, when I say back in the day, I'm talking, 30s, 40s, 50s, that time frame. You gotta understand, we had slide rules. We did not have, these computers and calculators that could do complex structural analysis for us. And so these pin and hangers, for one, you never ship, regardless of computers, you don't ship a 500-foot long bridge in one 500-foot long beam. You ship it in pieces and you assemble it, right? But these pin and hanger connections resulted in a structure that adhered to the analysis simplifications that we made during the analysis phase. So if we assumed this to be a hinge, this actually behaved like one. And one of the reasons that we placed these hinges inside the structures is to make them solvable by hand, okay? And that'll become, that part will become clear actually pretty soon when we start classifying structures. So if we wanted to maybe a more modern real world example of a hinge might be something like this. An I-beam that's connected via the web, but not the flanges, okay? It would transmit shear, but it wouldn't transmit moment, okay? Now to be clear, we really don't use these anymore. You'll see these in a lot of older structures, but we do use internal releases as an analytical tool for some other types of analyses we'll do later. For example, we'll use internal releases for influence lines and what have you. And we still do that today, so. But again, that's stuff for later. We will walk before we can run. Okay, everybody with me so far? Let's talk about structural classification. Make sure we're good on time. I'm great on time. Okay, I particularly want to talk about the two questions which I think are most important, which is whether or not a structure is stable and whether or not a structure is determinate, okay? I might go a little bit around the bend to define these, but when it's all said and done, you'll understand what they mean, okay? So let's go back to one of our favorite subjects, Engineering 213, statics, right? By the way, I just want to make this abundantly clear for everybody in the room. 3 letters we will not be dealing with in this class are I, J, and K. No cross products, no dot products, none of that, okay? Unless if you would like me to.
No, you're good.
You sure?
You're great.
Let me throw a unit vector in there. I can throw that in there if you want.
No.
Okay, that's what I thought. But we are going to be using equations of static equilibrium. We're just not going to be doing this using vector notation. Okay, we're going to make the analysis tools less cumbersome in here, but we're going to use those tools to analyze more real deal structures. So that's sort of the idea in here. Okay. So if we just generalize static equilibrium, we have all 3D systems have to satisfy 6 equations, 3 force equations, 3 moment equations, right? The idea is that the sum of forces in each direction, each cardinal direction must be 0, and the sum of moments in each cardinal direction must be 0. Now, we typically in civil engineering applications resolve that into a 2D model. And so in 2D, we have 3 equations of equilibrium. The sum of forces in the x direction, the sum of forces in the y direction, the sum of moments. We will be using those equations all semester. So it's just, that is going to be our lifeblood in here. Okay? Let's just look at a hyper basic problem. Okay? This is day 1 structural analysis. I have a beam. Okay? It has a pinned boundary condition and it has a roller boundary condition. So the pinned boundary condition has 2 support reactions that are unknown. The roller has 1. With me so far? By the way, if you ever hear me refer to a beam or a structure as simply supported, a simply supported structure is one that has a pin roller boundary condition type like this. Pin on one end, roller on the other. In other words, no fixed supports. That's kind of what that means. So if I look at this structural system, I have 1, 2, 3 unknowns, right? 3 quantities that are unknown. To address that, to solve for those unknowns, I have 3 facts, 3 tools that I can start applying. And that is that the sum of the forces in the x direction must be 0, the sum of the forces in the y direction must be 0, and that the sum of moments in the screen must be 0. Okay, so I have, so if I were to compare what I'll call the number of unknowns to the number of knowns, they'd be identical. Everybody with me on that? So the number of unknowns equals the number of knowns. In this scenario, I could figure out what AX is, what AY is, and what BY is using only statics. I don't need anything else. So far, so good? We would say that this structure is a structure that is statically determinate. Okay? Now, to be clear, that analysis, that idea extends not just to external equilibrium, but internal equilibrium as well. Okay? For example, one of the things that we're going to move past real quick in here is we're going to move past external equilibrium and we're going to look at internal forces. For example, okay, I am sitting here on this table. Okay? Not only does the table legs have to provide forces to keep the table in equilibrium, but the table itself has to develop internal forces to keep me upright. Okay? And it is those internal forces that we would design for. I'll give you an example. Okay? So let's say that you don't like me very much. Okay? And you decide, okay, I'm going to break out the secret weapon of structural engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan. So which samurai sword. Okay. All right. I like it. Okay. Okay. And then you say, okay, I'm going to chop right through the table right here. Okay. What's going to happen to me? I'm going to fall down, right? What's going to happen to your grade? You get the point, right? Now, but let's continue this thought experiment. Why is that going to happen? Okay? Because when you chop through the table, what you do is you release from the table the ability to resist whatever was going on inside that table, right? So you cause an equilibrium issue, I fall down, right? One of the common tools that we're going to have at our disposal is the ability to cut a section. And that's why I sort of say the secret weapon of structural engineering is a samurai sword or a lightsaber if you happen to be a sci-fi fan. But the truth is, so if I have a beam and I just slice through it, okay, I propose that inside that beam there are unknown forces as well. And it's those forces which, as a structural engineer, would help me figure out, okay, how big does this beam need to be? How wide do the flanges need to be? How thick does the web need to be in order to safely resist those loads, right? So I cut through the beam and I say, okay, I assume that inside that beam there's an unknown axial force, an unknown shear, an unknown moment. So again, three unknowns. How do I figure out what those unknowns are? The internal equations of equilibrium. So whether or not I'm looking at external equilibrium or internal forces inside a structure, I still have a scenario right here where I can figure everything out using only equations of statics. So far so good? Okay, so what I'm saying is that whenever you have a situation where you can analyze the structure using nothing but statics, we have a name for that, and we say that that structure or that system is determinate. That's what a statically determinate system means, is that we can solve for everything going on inside that system with just statics, with just equations of equilibrium. So what about a problem where we have too many unknowns? We have more unknowns than we do equations of equilibrium. Do we see that in structural engineering? You bet. We see that all the time. We see bridges that are multi-span. We see complex frames and buildings that have way more unknowns than we do equations of equilibrium. Okay? What we would say is that that structure is indeterminate. Okay? Now what about the flip side? What if we have three equations of equilibrium and we only have two unknowns? Well, that system is unstable. Okay? So I'm going to give you some simple definitions for determinacy, indeterminacy, and stability, and I'm going to refine those definitions here in a little bit. Okay? But does everybody kind of get the idea of how we would classify a system as stable, determinate, indeterminate so far? So far so good? Okay. Now, I'm going to give you a formula, okay, because we're engineers, we like formulas, okay? So I propose that what we can do is calculate a degree of indeterminacy, a number that we can classify a structure with, and I will call that the degree of external indeterminacy. Now, why am I calling it the degree of external indeterminacy? Because later on, we're going to have degrees of internal indeterminacy. And we're going to have an internal indeterminacy for a truss, an internal indeterminacy for beams and frames and what have you. But the idea is for now, we're just looking externally at a structure. Okay? And so if I've got this formula, okay, but I'm going to give you a simple way of thinking about it. That IE equals the unknowns minus the knowns, okay? In other words, I am comparing how many unknown quantities I have to how many known quantities I have. So what are the unknowns in this case? The unknowns are R. R being however many support reactions I have in the system. And again, I'm looking externally at the system as a whole, okay? What about the knowns? Okay, well, I propose that the term knowns is E sub c plus 3. Why 3? Why is the magic number 3? Why isn't it 47? Why is it 3?
Is that how many equations we have?
Exactly, that's how many equations of equilibrium we have. Some of forces in the x direction, some of forces in the y direction, some of moments, okay? I'm also throwing this term in here, E sub c. E sub c stands for equations of condition. In a simple way of thinking that is just how many internal releases there are in the system. So in other words, if I have a hinge inside the beam, that's going to be an internal release, okay? Now, if I have an I value of 0 or an I value that is positive, I say that the structure should be stable. In other words, it should be determinate, should be indeterminate. And I use that term should be very carefully because a non-negative value of I does not guarantee stability, okay? Now, if it is negative, the structure is unstable. I don't care what's going on. If I is negative, the structure is unstable, period, okay? But if IE is non-negative, if IE is 0, or if IE is positive, it should be stable. But there are some caveats to that, okay? And the caveats are coming real quick. So far, so good? Okay. All right. So let's look at some basic examples. I'm going to get to the caveats here in a bit, okay? So let's look at this problem right here. Let's look at this problem, this top one, okay? Just a picture, I have to pose. Okay, so let's take a look at this top one. I have 2 roller supports, so 1 reaction apiece, right? I have 2 reactions, and I have 3 equations of equilibrium. So if I plug and chug into this equation, 2 minus 3, I get -1. Now I'm telling you that a negative value of I means instability. But let's just take the math and move it away. Let's just look at the structure. Can anybody tell me why the structure is unstable? It's a skateboard. It's just going to roll, right? The moment that I take a load and I apply a load laterally, it's just going, whoop, it's just going to go, right? That's what instability means, okay? An unstable structure will not go back to its original shape after a load has been applied. You apply a load, it will freely deform. That is instability, okay? This structure is fine, okay? Structure is stable and statically determinate. And it's determinate because I've got 3 reactions and 3 equations of equilibrium. 3 minus 3 is 0. This structure is very indeterminate, okay? Because I have 1, 2, 3, 4, 5 reactions, 3 equations of equilibrium, so I get an I value of 2. So the way that we classify that is we would say that this structure is stable and statically indeterminate, and then it is customary to say that it is indeterminate to the 2nd degree. Why 2nd degree? Because I is 2, okay? The reason why that's important is because the higher that number is, the more number crunching you got to do to be able to solve it, okay? So if you were to ask me to solve a structure that I had an I value of 1 by hand, I'd go, okay. If you told me I had to solve a structure of I equals 47 by hand, I would go, who hurt you? Why would you do that to me? That would be painful, okay? All right, everybody good on this? And by the way, these notes are on Blackboard. Every one of these slides are on Blackboard, so if you miss anything, no worries. Okay, now like I said, a non-negative value of I does not guarantee stability. So what does guarantee stability? Okay, well, a structure is stable. For a structure to be stable, 3 conditions have to be met. First is I has to be non-negative, but you got to meet these two conditions as well. Okay. The first condition is that the reactions cannot all be concurrent, and the second is that the reactions cannot all be parallel. Let's take a look at this one. Let's take a look at this structure. If I calculated I for this structure, what would I get? I'd get 1. But is this structure stable? It's just a skateboard, right? It's just a skateboard with more wheels. How do we scientifically say that it's unstable? It has 4 reactions, and all of those reactions are parallel. That's what that means, okay? Now, here's one for you. Let's take a look at this. This structure also has an I value of 1. But is this structure stable? I say no, because all the reactions all meet at a common point. The reactions are concurrent. If I were to take this and turn it, it would freely deform, okay? This is sort of like a bicycle wheel. Like imagine I had a bicycle upside down and I had a wheel there. It would just spin, right? It wouldn't resist moments, okay? Does that make sense? If the reactions are all parallel, they can't resist a lateral force. If the reactions are all concurrent, they can't resist a moment, okay? That's the issue, okay? So we would say both of these structures are unstable. Okay. So far, so good? All right, and then the last little detail is about the equations of condition. So the internal releases, what they do is they make the structure solvable. Now the way that they do that is, so for example, if I look at this structure, okay, I have 1, 2, 3, 4, 5 reactions. It's indeterminate to the second degree. But if I throw a hinge in there, it reduces the indeterminacy by 1 degree. In fact, if I throw 2 hinges in there, the structure becomes determinate. The reason why is because if I break out my samurai sword or lightsaber and I cut right through that hinge, I know that the internal moments at that point are 0, because that's what a hinge is. A hinge tells me that I know that the internal moments right there, that the equation for that condition right there is that the sum of moments are 0, okay? That's what that tells me, okay? So this is how engineers back in the day would take a 3-span bridge and make it solvable. They would just throw some hinges in there, okay? Does that make sense? So far, so good? Let's do some examples. Okay, so I put a post on Teams on how to open the notebook. Did everybody see that? So if you open Teams, what you can do is go to the class that it's got a big I-beam icon. Go to the class notebook. And then you go here on the very left. And then you go to content library. And in that first folder, you'll see all the problems. Anything I put here on the screen, you all will be able to access 24/7. So I have this open up right here. Okay. All right. So let's see how we're doing. Let's see how we can walk through this. I'm going to walk you through the first one, and then I'm going to have you help me with the others. Okay? So let's take this first one. Let's look at example 1. Okay? So example 1, I have sort of this like overhanging beam, but I've got a couple rollers here. So this is how I'm going to go about this. So this first reaction, this is a hinge. So I'm going to say that it has 1, 2 reactions. Okay? This is a roller and this is a roller. So I'm going to say that this has 1 reaction and 1 reaction. Now, one thing that is worth mentioning is that I am drawing these reactions upward. When we start doing analyses, one of the things we'll have to do is make an assumption as to whether or not that roller reaction is upward and whether or not it's downward. We're going to make an assumption, and if we find out that assumption is incorrect during our calculations, it does not mean we need to develop significant emotional distress. It just means that we assumed upward, and if we get a negative answer, it means the answer is downward. So in statics, that probably didn't happen all that much. In here, it very well might. Okay, so I'm saying that now to sort of address that. Okay, So in this problem, I'm going to have an R value of 4 because there's 1, 2, 3, 4. And then I'm going to have an E sub C value. I can do better on that. I'm going to do an E sub C value of 0 because there are no internal hinges. Okay? So remember, our equation that we're going to use is R minus E sub C plus 3. That's the equation that we're going to use. So therefore, I is 4 minus 0 plus 3, which is 1. And I see here that my structure passes the test of the reactions not all being concurrent and not all being parallel, because I mean, like, these are concurrent, but that one isn't. And I've got parallel reactions, but that one's not. So they're not all concurrent or not all parallel, so this one's fine. So how I would classify this structure is I would say it's stable and statically indeterminate. And I would say to the first degree. Is my handwriting coming through clearly? Okay. If it's not and you point it out, you'll hurt my feelings, but then I'll do my best to clear it up. That was a joke, not a very funny one. Okay. All right. So that's the first one. Everybody with me so far? Okay. Now I'm going to need your help on the second one. So I'll guide you through a little bit, but I need some interaction here. So help me out. For this second one, I need to determine an R value and an E sub C value. Let's start off with E sub C. What's E sub C for the second one? 3, because I have internal 1, 2, 3 hinges. Okay? Now, can somebody tell me what R is? 6. Okay? Do I have a second on that? Yeah. Okay. I do that a lot. I'll ask a question, then I'll get somebody to second me like it's a motion. Make sure everybody's paying attention. All right. So the reason why is because there's 1, 2, 3, 1, 2, 3. So R is 6. So what do we get for IE? Oh, nope, that's not 0. That's 3. So what's IE? 0. Is the structure stable? Yeah, it's stable. That's not a problem. So we're going to say stable and statically determinate. Okay. All right. All right, any questions on that? I don't want to move on if everybody's got any questions. Here's the thing about questions in my class. If somebody asks a question, chances are other people had it too. And whether or not it's scholarships, your parents, your pocket, or loan, somebody put cash money on the table for you to be in this room. So you got a question, you ask it, okay? Sound good? Don't hesitate. All right. So, how about example 3? Somebody tell me what's going on with example 3. It's unstable. Why do you say it is unstable, sir?
All 3 reaction courses are parallel.
There we go. So if I identify those reactions 1, 2, 3, what I can say is all reactions are parallel, therefore unstable. Okay? Whenever you have a structure that is unstable, I do not care what I is, I do not care what anything is, the structure is unstable. If a bridge falls down and kills somebody, nobody's going to go, wait, what was the I value? You know, so it's the truth. No, in all seriousness, it doesn't matter what we don't have structures that are unstable and indeterminate to the 7th degree. I don't care. It's unstable. So, sound good? All right. Last one. Okay, so let's see what we got going on here. All right. So I'm going to just stand here and have you all tell me what to do. Tell me what to do.
R is 6.
R is 6. Okay, so I think you're saying 1, 2, 3, 4, 5, 6. So R is 6. E is 2. So therefore, what is that? 1. So tell me what to write. How would we classify this structure?
Stable and statically indeterminate first degree.
There we go. So stable. All right. I can do better than that. Hold on. That's close enough. All right. Not too bad, right? Yes, sir.
How did you E sub C value again?
The 2 hinges.
Oh, hinges are okay.
Yes, the internal hinges.
Okay,
Yes.
cool. Thank you.
Anytime there's an internal release, so later on in the semester, we're actually going to look at moment releases and shear releases. But for the first at least half of the semester, it's just hinges. So we will use shear releases for a very specific reason. It involves analyzing structures when the loads move, when the loads don't sit still, and it is a very nuanced analytical technique. Trust me, we'll do it a little later. All right, I have something else I want to show you before we leave. It won't take but a minute. Everybody good? Okay. All right, so I wanted to show you what you're going to find on Blackboard. So this is your first assignment. So these classification problems were pretty quick, right? So I just gave you a few more. That's all I want you to do. Just get a few more. Like I picked a few problems out of the textbook and I said just classify these structures, okay? Now, I imagine some of you are still waiting on your textbook to come in the mail. So what I did is on the following pages, I just included the screen caps from the textbook, okay? Now, to be clear, like if you look at problem 1 has 4 structures. I don't want you to do all 4. I only want you to do the ones that are here. It's like problem 2 has 3.2C. Just do structure C. Don't do all of them, okay? Just do the ones that are indicated in the assignment. Yes, sir?
Are you going to keep providing pictures for future homework?
I'll probably do it for the first couple weeks, and then I'll probably stop. So. I know what you're asking. I know what you're asking. I'll do it for a little while, and that's it. All right, everybody good? All right, for anybody that was late, I'll give everybody a chance one more time to scan the code, but that's all I got. I will see you all on Friday.